Hey everybody, welcome back. We are continuing our discussion about isocosts and isoquants to look at how firms determine what is the best combination of labor and capital to use in order to produce a certain amount of goods. So in the last presentation we saw that firms can choose a bunch of different combinations of labor and capital in order to produce a given amount of goods. In this presentation, we'll be looking at how do they decide what is the most efficient or cost-minimizing combination of labor and capital to use to produce. So here we have a graph where we've combined isocost lines with an isoquant. So the question is, which combination, so the red isoquant represents a certain amount of output. It doesn't matter, we can say this is an output level of 50 units or something like that. So the firm wants to produce 50 units. They can do that using, so here are two examples, a combination at point A or at point B of capital and labor. So point A is using less labor and more capital. Point B here is using more labor than point A and less capital. Both of them produce an output of 50 units. Which one is more cost effective? So I'll let you put that in. So of these 2 points, B is cheaper than A. It's on a lower isocost line. So here, B is cheaper than A. But then the question is B the best combination of capital and labor? So I'm going to let you put into PlayPosit. I want you to put in what you think are the coordinates or the combination of labor and capital that would be cost minimizing. Oh my goodness, my dog just farted. It's very smelly in here now. Okay. Oosh. Burns. It turns out that point C would be the cost minimizing combination of capital and labor. So that is, looks like right about 5.5 units of labor and just about 3 units of capital. So if the firm wanted to produce 50 units of output, that combination of labor and capital would be would cost the least amount of money and still produce 50 units of output. So graphically, it should not surprise you that the cost minimizing bundle is again going to be at a point of tangency. Points of tangency are very popular in this course between isoquants and isocost curves. So graphically, where the two types of the isocost and isoquant just barely intersect at one exact point. We're going to get into how to find this point mathematically. It's going to look very similar to how we found optimal bundles for budget constraints and indifference curves. So that math is going to be very similar. But again, it's going to rely on, at a point of tangency, the slope of the two functions is equal. So let's start digging into that. Okay. So we need some more numbers in order to make this example work. In this example, the output level is 4. So we want to produce 4 units. The wage rate is $15. The rental rate is $30. Oh, I'm going to use K. So point C is a point of tangency. The slope of the isocost and the rate of change of the isoquant curve are going to be the same. So the first thing we need to do is figure out the slope of the isocost line. So remember, the slope of isoquant or isocost curves. So that's the linear function here, the blue line, is, ooh, hello. I don't want to see the news of the day, so please go back to what I was doing. This is quite frustrating. Jeez. Okay, sorry about that. The slope of an isocost curve is W over R, the wage rate over the rental rate. So here, W is 15, R is 30, so the slope of the isocost curve is going to be 15 over 30. Okay. Okay, so we need to find the rate of change of the isoquant. So that's the red function in here. So in order to do this, you're going to need a function for the isoquant. That's given right here. Quantity is equal to the amount of labor raised to the 1/2 times the amount of capital raised to the 1/2. So just like when we were dealing with indifference curves, the rate of change of an isoquant is going to be the derivative of the quantity function with respect to labor divided by the derivative of the quantity function with respect to capital. The slope of a isoquant is called the marginal rate of technical substitution. When we were looking at indifference curves, the rate of change of an indifference curve is called the marginal rate of substitution. This is called the marginal rate of technical substitution because there's like technology involved with producing stuff, and we need a different term for it. And it's the marginal product of labor over the marginal product of capital. Remember, the marginal rate of substitution for an indifference curve was the marginal utility of the horizontal good divided by the marginal utility of the vertical good. So this is very similar. So we need to apply the power rule to this function with respect to labor first, and then to capital, and then divide the two. I want you to go ahead and try that and see what you get. I'm going to pause it and work it out on the screen here. Okay, so here's the work to find the marginal rate of technical substitution. Start here. This is finding the marginal product of labor. You take the derivative of quantity with respect to labor. Bring it down, you get 0.5 L to the negative 0.5 times K to the 0.5. Again, since we're treating L as the variable, K here is treated as a constant, so you just don't do anything to it when you take the derivative. Then I just simplify it and move the negative exponent down to the denominator. Then here, I'm finding the marginal product of capital, so I'm taking the derivative of quantity with respect to K. You basically get the same thing, except for now it's the exponent on capital that's negative 0.5. And again, I just simplified so that the negative exponent's in the denominator. So once you have the two marginal products, you just divide the marginal product of labor by the marginal product of capital to find the rate of change of the isoquant. So that's what I'm doing here. This term is the marginal product of labor. Instead of doing marginal product of labor divided by marginal product of capital, to save some space, I just skip to the step where you multiply by the reciprocal. So this second term is just the marginal product of capital, but flipped. Then when you simplify, the 0.5 coefficients cancel out. You get k to the 0.5 times k to the 0.5, which is just k. And then you get L to the 0.5 times L to the 0.5, which is just L. So the marginal rate of technical substitution is just k over L in this situation. So if you want to find the rate of change of this isoquant at this point, you would just plug in the amount of capital at that point and then divide it by the amount of labor at that point, and that tells you the rate of change at that point anywhere on this isoquant. Cool. Okay, here's the work for it again. Okay, so now we want to set the marginal rate of technical substitution equal to the slope of the isocost. So remember, the slope of the isocost was 15 over 30. Marginal rate of technical substitution was just K over L. Set them equal to each other. Yada, yada, yada. So I want to plug in. So now I want to use the rule that we got here. I'm going to use that to substitute in. So if we simplify this, we get 1/2 equals K over L. 2K equals L. So I want to use that to substitute into our isoquant function, but I don't want to deal with the fractional exponents or the decimal exponents, if you want. So the first thing I'm going to do here, so remember we were told that we wanted to produce 4 units of output in the beginning of the problem, and this is just the quantity equation. To clear these 0.5s, I'm just going to square both sides. Remember, 0.5 power is the same thing as the 1/2 power, which is the same thing as square root. So to get rid of them, I just need to square both sides. When you square both sides, just to make this clear, all right. And then when you solve that, you get K is equal to 16 over L. So this was the relationship we got on the previous slide when we set marginal rate of substitution, marginal rate of technical substitution equal to the slope of the isocost line. So I'm just going to replace the K here with what we got K was equal to, 16 over L. You get 1/2 equals 16 over L squared. And then cross multiply, you get L squared equals 32. And you take the square root of both sides, and you get that the optimal amount of labor to use in this situation is 5.657 units. And then once you have L, you can go back and substitute in, do 16 divided by L to get the optimal amount of capital. So that gives you the coordinates of point C. So that's how you find the optimal combination of capital and labor to use mathematically. So I think the next slide is an example problem. So I'm going to put it up and let you work through it. Yep. Okay. So we want to find the cost minimizing combination of capital and labor to produce 100 units. You have a production function here and the wage and rent rate. So the first thing I want you to do is to find the slope of the isocost line. Okay, the slope of the isocost function is 3/2. It's up here where I did the work. Remember, the slope of an isocost is W over R. Now I want you to find the marginal product of labor. So we need to find the marginal rate of technical substitution. In order to do that, we need to find both the marginal product of labor and the marginal product of capital. Let's start with labor. Okay, here's the work to find the marginal product of labor. Took the derivative with respect to L, brought down the 0.75, subtracted 1 from the exponent on L, left K the same, and then simplified. Okay, now find the marginal product of capital. All right, here's the marginal product of capital. Brought down the exponent from capital with 0.25, reduced exponent by 1, left labor the same, and simplified. Okay, now find the marginal rate of technical substitution by dividing the marginal product of labor by the marginal product of capital. Okay, here you go. Marginal product of labor was here. Then I flipped the marginal product of capital to multiply. 0.25 goes into 0.75 3 times, and you get that the marginal rate of technical substitution is 3K over L. Okay, now we want to set the production function equal to 100 and